Today we're going to talk about transient analysis of first order circuits. So let me write that down really quickly. Where a first order circuit is a circuit that's containing one energy storage element, so one capacitor or one inductor. And let me modify that slightly by saying, really it means that if there are multiple energy storage elements, so multiple capacitors or multiple inductors, we have to be able to shrink the circuit down to one equivalent capacitance or inductance, okay? So I'm going to try to teach this a little bit differently than I normally do, so bear with me. But I want you guys to consider a simple circuit, okay? So let's say that we had a circuit like this where we have some DC voltage, and then here we have a switch. And I'm drawing this in such a way as to try to illustrate that at one particular point in time, which I'm going to call t is equal to 0, our switch is opening up. On the other side of the switch, I'm going to put a resistor. So what I want to ask you guys, let me define the voltage drop across the resistor like so. So this is VR as a function of time. I want us to think about what the plot of that resistor voltage might look like for points in time before 0, meaning before our switch opened up, and then for points of time after our switch opened up. Does anybody have any thoughts on what might be going on here?
So with the switch open, the resistance would be infinite.
So we're not looking for the resistance, we're looking for the voltage drop. The resistance is just going to be R, because the resistance, we are working in a linear time invariant system, so none of our component values can change. So like, what do you think the voltage drop across the resistor is going to look like for time greater than 0?
There wouldn't be any voltage drop across it because there's no voltage going through it.
Exactly right. So there's no current flowing through the resistor for t greater than 0, so there can't be any voltage drop across it. That's a perfectly acceptable answer. So everywhere from 0 and beyond, we would see that our voltage is at 0. What about before our switch opened up? Excuse me.
Just VDC.
VDC. Absolutely right. So if this level corresponds to VDC, we would see that the voltage drop across the resistor is VDC until the switch opens, and then it would be able to instantaneously fall down to 0, and it would stay 0. So this is effectively, this circuit would be almost exactly like what we'd expect in a flashlight if we were trying to turn the flashlight off. Now, I want to make a small modification to our circuit, and then we're going to have the same discussion, okay? And that modification is adding an energy storage element. So I'm going to have my DC voltage source just like I had earlier. I'm going to have my switch, which is opening at t is equal to 0, just like earlier. But now I'm going to have my resistor R. And in parallel with that, I'm going to have some capacitance C. And I'm going to call the voltage drop across those two elements in parallel V of t. And over here to the right, we're going to make a plot and try to figure out what's going on again. So on our vertical axis, we'll have V of t, and then our horizontal axis is once again time. So let's start explicitly here with what's going on before our switch opens. So what do we think V of t should be?
VSC.
VDC, so our DC source voltage. For those of you that aren't quite on board with that, let me explain things really quickly, okay? So when our switch is closed, and if we assume that it has been closed for a very long time, then our circuit looks like a DC circuit. And in a DC circuit, we learned in Wednesday's class meeting, today's Wednesday, Monday's class meeting, that a capacitor behaves like an open circuit in a DC circuit. So for t less than 0, the circuit that I've drawn down here with the resistor and the capacitor in parallel is effectively the exact same circuit as above, because the capacitor isn't doing anything, it's behaving like an open circuit. Okay. Now, let me actually make a note here. So I mentioned that prior to t is equal to 0, our circuit is behaving like a DC circuit. So I'm going to call this specifically a DC steady state condition. Okay. Now let's figure out what's going to go on after our switch opens up. Okay, so this is kind of the new stuff here. So does anybody have any thoughts on what might happen?
The voltage drop is going to gradually decrease.
So
First, it'll be the same because the capacitor is charged up.
excellent job. So I was expecting somebody to say that the voltage would fall to 0, and it will over time, but you're 100% right that it's going to gradually decrease to 0. And the reason why it's going to gradually decrease to 0 instead of instantaneously decreasing to 0 is because, once again, on Monday, we learned that the voltage drop across a capacitor cannot change abruptly. So if we had an oscilloscope or some sort of measurement tool, what we would see is that the voltage drop across our capacitor and resistor in parallel is going to gradually decay. And then after some amount of time, it will eventually settle back down to 0. So let's explain why it settles back down really quickly, okay? So at t is equal to 0 minus, our voltage V of t will be exactly equal to VDC. So the instant before our switch opens up, the voltage drop across, I'm sorry, what was that? Okay, so the instant before our switch opens up, the voltage drop across our capacitor will be VDC. And the instant after the switch opens up, which I'm going to call t is equal to 0 plus, our voltage will continue to be VDC. Now, this is only true because we're dealing with the voltage drop across a capacitor. If it was the voltage drop across a resistor, it could instantaneously change. If it was the voltage drop across an inductor, it could instantaneously change. But we know for sure that in a capacitor, the voltage drop cannot change abruptly, because to do so would require an infinite amount of energy to be transferred. Okay. Now, at what I'm going to call t is equal to infinity, and this really just means a very long time after our switch has changed state, we should see that the voltage drop across our capacitor settles to zero. So let's think about what's going on. So at t is equal to 0 minus, our capacitor has a voltage of VDC, and we know that whenever there is a voltage drop across our capacitor, regardless of whether that voltage is positive or negative, our capacitor is going to have some amount of stored energy, right? We know that the energy stored by a capacitor, let me just put it up here to remind you guys, is given by 1/2 C times the voltage drop across the capacitor squared. So at t is equal to 0, the voltage drop across the capacitor is non-zero, so there's energy stored in the capacitor. Well, when that switch opens up, that resistor is going to gradually convert the energy that was stored by the capacitor into heat. And that process, that energy conversion, takes time. And so that's why we see the voltage drop gradually decay toward zero. The rate at which the energy is transferred from the capacitor to the resistor is dependent on the value of both the resistor and the capacitor, and we'll see that shortly when we derive some things. So what we're looking at here is a system where we had some amount of energy stored, and then after a specific point in time, we stop replenishing that amount of stored energy and allow it to be dissipated into our system. Okay. So let me make a couple of marks here really quickly. So this is t is equal to 0. Way out here on the right-hand side, after our voltage has decayed down to 0 again, I'm going to call this time infinity. And again, all I mean by t is equal to infinity is just a very long time after our switch has changed state. So once our voltage is back down to 0, and it's going to effectively stay at 0, we are at a DC steady state condition yet again. This time in between these DC steady state conditions is what's known as a transient condition. And that's what we're trying to mathematically model today. So transient simply means that our circuit or system is undergoing a change. Okay, so we still have a DC circuit for t less than 0, and we have a DC circuit for t greater than infinity. But between 0 and infinity, we've got something weird going on that we are able to physically describe. But now we're going to work on mathematically describing what's happening. Okay. So let's work on that mathematical description. Okay. So for t is greater than 0 plus, so this is all points in time during the transient condition, our circuit is going to look like this. So we still have our DC voltage source, but it is disconnected from the network that contains the resistor and the capacitor. So that's why I'm drawing that open circuit terminal up on the top. And then over here on the right, I'm going to put my resistor R in parallel with my capacitor C. Here's my voltage, V of T. So before I add anything to this diagram, does everybody agree that this is what our circuit will look like for all points in time after T is greater than 0 or after our switch opens up? Okay. So what I'm going to do now is simply identify a couple of currents, right? So this is the current that's flowing through my resistor, and this is the current that's flowing through my capacitor. And if I were to apply KCL at the top right node, what I would see is that our resistor current IR of T and our capacitor current IC of T have to add together to make 0, because Kirchhoff's current law always has to be satisfied. Now I can express both of those currents in terms of the voltage V of T that's common to the resistor and the capacitor, right? So for the current flowing through the resistor, that's simply Ohm's law, right? So we're going to have V of T divided by R. And for the current flowing through the capacitor, we're going to use our derivative-based relationship. So the current in a capacitor is equal to C times the derivative of the voltage across the capacitor with respect to time. That's equation 1 for Monday. Okay? And this will still be equal to 0. I know that the overwhelming majority of you probably have not yet had Math 245, so I don't want you to get too intimidated by this statement. But what we have here is a linear, homogeneous, first order differential equation. Okay. So once you take Math 245, you will understand and gain tips and tricks on how to solve this type of equation very regularly. But we are going to have to use a little bit of intuition because most of us haven't had that particular math class. So let me describe what our process is going to be. Okay. Our ultimate goal here is to figure out what V of T is doing between T is equal to 0 and T is equal to infinity. So we can see from this expression that we have our voltage multiplied by a coefficient of 1 over R plus the derivative of our voltage multiplied by a coefficient of C has to equal 0. So what we're looking for is a mathematical waveform or function where the function plus its derivative might add together to make 0. Does anybody have any thoughts on what functions might do that?
Trig functions?
So trig functions is a common guess. So let's think about things really quickly here. So over on the right-hand side, and you don't necessarily need to write this down because I'm going to wind up erasing it in a moment, but let's say that V of T was just cosine of t. Let's make it really, really simple, okay? What would the derivative of v of t then be?
Negative sine of t.
Negative sine of t. So does cosine minus sine of t equal 0 for effectively all time? I would argue that it pretty much will never equal 0 because cosine and sine are 90 degrees out of phase with each other. So if I were to plot cosine, it would look something like this. And if I were to plot sine, it would look something like this. And if I add these two functions together, point by point, I don't think there's a time when they're going to be 0. Or if there are times when it's going to be 0, it's just going to be very, very small points in time, but it's not going to be generally true. So trig function, very, very common guess. If we were dealing with the function plus its second derivative, cosine and sine functions would both be perfectly acceptable answers. But because we're dealing with the function and its first derivative, we've got to think of something else.
Logarithmic.
So
I'm basing that off of your graph that you drew earlier with the decay of the voltage drop.
So I'm going to do the inverse of logarithmic. I'm going to do exponential, right? So we are going to guess that our voltage waveform v of t will be of the form a, where a is an arbitrary coefficient. We'll sort out what it is in a little bit, multiplied by our function e to the st, where s is what's called the eigenvalue of our system, and it's going to represent how our signal decays, or the rate at which our signal either decays or exponentially increases. Okay? So hopefully we can all agree that the derivative of dv by dt should be s times a e to the st. And so it seems to me that our function and its first derivative are of the exact same form, just a coefficient multiplied by an exponential function. So it stands to reason that we should be able to combine these together to make 0 somehow. And that's exactly what we're about to do. Okay? So if I put in my guess value here, I'm simply going to substitute this information into our first order differential equation. And so what I'm going to have is 1 over r times a e to the st plus s times c a e to the st is equal to 0. Now I'm just going to take some common factors out, right? So we can see that there is a common factor of a in the first term and the second term. So I'm just going to pull that out. And there's also a common factor of e to the st in the first and second term. So I'm going to pull that out. And what's left in the middle will be 1 over r plus s times c. And I need this expression to be equal to 0. So let's talk about the different ways that can happen. Okay. So the most obvious way that it can happen is if our coefficient A was equal to 0. Because if our coefficient A is equal to 0, then everything is 0. So while that is a solution, it is what's called a trivial solution. And it effectively represents our system if we never stored any energy in our capacitor, which we know isn't true. So while it is a solution, it's not really the one that we are looking for. E to the st will approach 0 if s is a negative quantity, but it'll never quite get there. So that's really not the thing that we're looking for either. So what we're going to rely on is this part in the middle here. And this is what's known as our characteristic equation. Or characteristic polynomial for our system. This is a simple first order polynomial, so it's not going to be particularly difficult to solve. So we have the expression 1 over r plus sc, and we want to know when that is 0. So let me just write that down over here. So 1 over r plus sc is equal to 0. So that is true when s is equal to what?
When you have negative C over R?
Not quite, right? So let's play around with this really quickly. So if I divide both sides by c, that'll give me a factor of 1 over rc plus s is equal to 0, because 0 divided by c is still 0, right? So it seems to me that if s was equal to negative 1 over rc, then our characteristic equation is 0. Anybody got a problem with my small amount of algebra there? All right. So we've just figured out what our eigenvalue S for our system is. So our guess value is now going to be kind of updated to say that V of t is equal to A e to the negative t divided by RC. So that 1 over RC is effectively telling us what our rate of decay is. And we know that it is indeed a decay because it's negative. Now we need to figure out what's going on with A. And so this is where we're going to have to bring our capacitor relationship back in, right? So V of t here is a mathematical model for the voltage drop across a capacitor. And we know that the voltage drop across a capacitor cannot change abruptly. So our transition in our system is occurring at t is equal to 0. So if we evaluated this function at 0, we would have v at 0 is equal to a e to the negative 0 over rc, which is just a times 1. So our coefficient a is just whatever was going on with the capacitor at 0. I'm going to make a very slight change in this designation here. And instead of saying 0 generally, I'm going to explicitly say what's going on at t is equal to 0 plus. And so that changes or finalizes our voltage waveform to be V at 0 plus e to the negative t divided by RC. So this is what the voltage drop across our capacitor is doing as a function of time for t greater than 0 plus. Notice up here, all of this derivation was for what's going on for t greater than or equal to 0 plus. Okay, so a couple of things here. First, we derived this very generally. We didn't use a single number except 1 and 0 the entire time, right? So we didn't make any assumptions on what the value of the resistor might be, nor did we make any assumptions whatsoever or constraints on what the value of our capacitor might be. So this equation is valid for literally any circuit that contains a resistance and a capacitance that is undergoing a transition. Regardless of how simple or complex it is, if we can simplify everything down to a single resistance and a single capacitance, this equation works. So let's look at our in-class assignment problem here. Let's do problem 2 first, because it's specifically what I'm going to call from now on an RC circuit. And our ultimate goal here is to figure out what the resistor, sorry, that's not what I meant to do, voltage is doing as a function of time. So I'm going to introduce you guys to an analysis process. So this is pretty similar to what we did when we were doing nodal and mesh, in as much as I'm going to give you a series of steps. And if you do those steps in the order that I ask you to do them, you will get the right answer 100% of the time, okay? So our first step is going to be to analyze the circuit at t is equal to 0 minus. So this is the moment in time immediately before the switch changes state, okay? So at t is equal to 0 minus, we are going to have a circuit that looks like this. So here we have a 2 kilo ohm resistor in series with a 4 kilo ohm resistor. We have a current source that is 4 milliamps direction up. We've got a 1 kilo ohm resistor over here. And at t is equal to 0 minus, our switch is closed because we're told the switch has been closed for a very long time before opening. So my switch is just going to look like a short circuit. I have a 2 kilo ohm resistor over here. And then on the right-hand side, I'm going to put my capacitor. But I'm not actually going to put my capacitor here because we are at DC steady state. We're at time before our switch change states. So I'm just going to replace my capacitor with its DC equivalent, which is just an open circuit. Here's my resistor current at IR of 0 minus. That's what I'm interested in. But I'm also going to be paying attention to what's going on with my capacitor voltage at 0 minus as well. And that'll become more obvious when we get through subsequent steps in our analysis procedure. Okay. So our ultimate goal here is to figure out what IR at 0 minus is and what VC at 0 minus is. Does anybody have any thoughts?
Mesh analysis?
So we definitely could do mesh analysis to find IR at 0 naught. The reason why I am hesitating here, and let me explain my thought process, is so to the left of the 4 milliamp source, we have a 2 kilo ohm resistor in series with a 4 kilo ohm resistor. So we could lump those together as a 6 kilo ohms of resistance in parallel with that 4 milliamp source. On the right, we have a 1 kilo ohm resistor that is, for all intents and purposes, connected in series to a 2 kilo ohm resistor, because we know that no current is going to branch off and flow through that open circuit representing our capacitor. So while we could do mesh analysis, which would set up a system of equations and all of that kind of good stuff, we're going to get the same result if we do current division. So I'm just going to do current division. So our current division relationship will be IR at 0 minus is going to be our known current of 4 milliamps. In the numerator, I have the reciprocal of the branch that I'm interested in, and that branch is 1 kilo ohms in series with 2 kilo ohms. And then in my denominator, I just have the reciprocal of my different parallel branches. So that's going to look like 1 over 2 kilo ohms plus 4 kilo ohms plus 1 over 1 kilo ohm plus 2 kilo ohms. So I'm going to do a little bit of mental math here because my office is dark and I don't see a calculator directly in front of me. So this looks like 1/3 over 1/6 plus 1/3. So that would be like 2/6 over 1/6 plus 2/6. So that would be 2 over 3. So 2/3 times 4 milliamps is going to give me 8/3 of a milliamp. And if you guys want to use a calculator to verify that, you are more than welcome to do so. So, assuming I've gotten that resistor current correct, and I know for a fact that I did, because 8/3 is 2.667 milliamps, how would I find that capacitor voltage VC at 0 minus?
It'd just be the voltage drop across that 2 kilo ohm resistor?
Exactly right. So what do I need to do, Austin?
It would be your IR times the 2 kilo ohm resistor.
Yep. So that's just going to be 8/3 of a milliamp times 2 kilo ohms gives me 16/3 of a volt. So before we move on from this step, does anybody have any questions about any of the analysis we did to determine either of those two quantities? All right. So because there's not a ton of room on this page, I'm going to make a table up here that's going to kind of keep some of our information. So IR at 0 minus, or actually, let's do it this way. So IR of t and VC of t. And then on this side, we're going to have times. So at 0 minus, we had 8/3 of a milliamp, and VC was 16/3 of a volt. All right, am I okay to erase my work for step 1 and replace it with step 2? Nobody's telling me not to, so I feel like I'm good to go. All right, so step 2 is going to be to analyze the circuit at t is equal to 0 plus. So this is the moment after the switch changed states. So here's our 2 kilo ohm resistor, our 4 kilo ohm resistor, our 4 milliamp current source, our 1 kilo ohm resistor. At this point in time, our switch is open, so that's why I'm putting an open circuit there. Here I have a 2 kilo ohm resistor through which we have our current IR at 0 plus. And over on the right-hand side, we're going to have our capacitor. Now, I want to be very clear about this because I'm about to do something that's going to seem incredibly weird. But we are looking at this circuit at one very specific instant in time, okay? So we're looking at the circuit immediately after our switch has opened up. So we know that our capacitor voltage cannot change abruptly. So that means that if the voltage drop across the capacitor was 16/3 of a volt at t is equal to 0 minus, it has to continue being 16/3 of a volt at t is equal to 0 plus. Is everybody okay with that statement? Nobody is opposing me, so I'm going to assume that you're all on board. So we know that the voltage drop across the capacitor at t is equal to 0 plus is exactly 16/3 of a volt. We know nothing about the current that's flowing through the capacitor, nor does it even particularly matter to us. So what I'm going to do is I'm going to replace my capacitor with a DC voltage source that has the same polarity and the same magnitude as the capacitor voltage at t is equal to 0 minus. So that would be 16/3 of a volt, positive polarity on top, negative polarity on bottom, like so. The reason that I can do this is because at this very specific instant in time, our capacitor is functionally identical to a voltage source. It's providing a fixed amount of voltage regardless of whatever current is flowing through it. Okay. So now we just need to do our circuit analysis to figure out what IR at 0 plus is. Anybody have any thoughts on what we might do?
Would it just be 16/3 of a volt divided by the 2 kilo ohms?
Exactly right. So just Ohm's law. So 16/3 of a volt divided by 2 kilo ohms is going to give us 8/3 of a milliamp. So the current flowing through our resistor didn't change from 0 minus to 0 plus because it's directly in parallel with that capacitor whose voltage literally cannot change between 0 minus and 0 plus. So the voltage, the current flowing through the capacitor, the current flowing through the resistor doesn't have to be the same at 0 plus as it was at 0 minus. Only the voltage drop across the capacitor has to stay the same in this particular circuit. So any questions regarding that particular step?
So the voltage has to stay the same here because it's the instant after and the capacitor cannot instantly change in voltage.
Exactly right. So we know from our past 2 lectures that the voltage drop across a capacitor cannot change abruptly, and the current flowing through an inductor cannot change abruptly. So we're going to do something pretty similar when we work inductor problems here in a few minutes. But for now, since we've just learned about effectively how an RC circuit works, we're only worried about making sure that the capacitor voltage stays constant between t is equal to 0 minus and t is equal to 0 plus.
Okay, thank you.
No problem. Any other questions on this step?
So Dr. Harvard, so it is based on this, it is okay to think of a capacitor as just like a buffer.
I don't know what you mean by buffer.
Like you're storing it up, storing it up, storing it up, and then whenever you shut the supply off, it just gradually drains.
So that is what's happening in the circuit over time for sure. So you're saying a buffer, like kind of a memory buffer thing where it's just holding on to a piece of information. Yes, but at this point, I just want to be really clear. We're only looking at the circuit at this very, very specific instant in time, which is why we're allowed to replace our capacitor with a voltage source. Immediately after this instant in time, the voltage drop across our capacitor is going to start to gradually decay, dependent on the equivalent capacitance and equivalent resistance in the circuit. We'll get to that step here in just a moment. I just want to be really clear about what it is that we're looking at right now. Any other questions or comments? All right. So I've put all of the pertinent information in my table. So now we're going to go to step 3. Step 3 is simply to analyze the circuit at t is equal to infinity. Okay. So our circuit isn't going to change a whole heck of a lot. Our switch opened up at t is equal to 0 plus, and it's going to stay open forever because we weren't given any information about it reclosing. At t is equal to infinity, we are at DC steady state once again, so we're simply going to replace our capacitor with an open circuit because a capacitor behaves like an open circuit in a DC circuit. So here is our capacitor voltage at infinity. And while we weren't particularly asked for it or anything like that, we're still going to keep track of it just in case. So does anybody have any thoughts on what our values at t is equal to infinity should be?
Zero.
0 for both. So 0 amps for our resistor current.
I grabbed on
I'm sorry, what was that, David?
Sorry.
No problem. So our resistor current is 0 amps and our capacitor voltage is 0 volts. And the most simple explanation for why that is, well, we no longer have any energy stored in our system, and neither of these two elements is actually connected to a voltage or current source, right? So at t is equal to infinity for all of the circuits that we're going to be dealing with today, everything that we're interested in is going to decay to zero. The reason I'm including this step is because on Friday, we're going to look at what's called the total response, which is what happens when we leave voltage and current sources connected to our energy storage element. And we're going to have to do this step then. So I'm just getting us in the habit of doing it now. But we should expect our analysis at t is equal to infinity to just give us zeros for today. Okay. Any questions on this step? All right. So our fourth step, actually, I can leave that there for now as well. So our fourth step is going to be to determine CEQ and REQ during the transient. Okay. So let me erase some things here really quickly. I'm going to put my capacitor back in just as a capacitor for a moment. 300 microfarads. Okay, so let me explain exactly what it is that we're doing here. So first, let's figure out what CEQ is, because that should be incredibly easy. Anybody have any thoughts on CEQ?
Microfarads.
300 microfarads. There's literally only a single capacitor in this circuit, so it can't be anything else. So that part's pretty easy. So CEQ is equal to 300 microfarads. Now, this is a step where I see a large number of mistakes from students, so I'm going to try to explain myself as best as I possibly can here, okay? When we're finding REQ during the transient condition, what we are doing is finding the equivalent resistance seen by our energy storage element during the transient condition. So during the transient condition, my switch is opened, which is why I have drawn it as opened. And we're just finding effectively the Thevenin resistance seen by the 300 microfarad capacitor. So how do we find the Thevenin resistance as seen by a particular circuit element? Does anybody remember how to do that?
Don't you just like make it an open circuit there and then analyze from there?
Exactly right. So we take the 300 microfarad capacitor out, leaving behind an open circuited set of terminals. And then we look in to find REQ, but we're missing one other thing. So when we are finding a Thevenin equivalent resistance, which is exactly what we're doing here, we need to make sure that we're looking at a dead network. So how do I make this a dead network?
Get rid of the 4 milliamps.
Exactly right. So how do I do that, Cameron? Do I replace, I turn off a current source by replacing it with a short circuit or an open circuit?
If I remember, it was a short circuit.
So we turn off voltage sources by replacing them with short circuits, because 0 volts is the voltage drop across the short circuit. We turn off current sources by replacing them with an open circuit, because the current flowing through an open circuit is 0 amps. All right, so what is the equivalent resistance that I see?
2 kiloohms.
2 kiloohms, exactly right. So, seen between these terminals, let me make this super obvious, just in case anybody isn't quite following. We have this node on the top. We have this node on the bottom, and then I'm going to put a node over here in blue. We can obviously, I hope, see that the 1 kiloohm, the 4 kiloohm, and the 2 kiloohm on the left are all in series, so that would look like 7 kiloohms. But that 7 kiloohms of total resistance isn't part of a closed current carrying path, which is why it's not contributing to the resistance seen by the capacitor. So effectively, because that portion of the circuit was disconnected from the capacitor, it doesn't make any difference to the resistance. Okay. So any questions about how we determined REQ here? All right. So now we're going to go to step 5. And this is our last step, for what it's worth. So step 5 is simply plug stuff into our equation. Okay. So the equation that we came up with earlier was the voltage drop across our capacitor, Vc of t, was whatever it was at excuse me, whatever it was at 0 minus for t less than 0 minus. And then when we derived things, we got Vc at 0 plus e to the negative t divided by Rc, where I'm going to put Req and Ceq here explicitly for t greater than or equal to 0 plus. Okay. So this is the equation that we are going to plug things into. So if I put in our numbers from the little table that I wrote, we're going to have 16/3 of a volt for t less than 0 minus, and then 16/3 e to the something. So let's figure that out really quickly. So 1 over Req times Ceq is 1 over 300 times 10 to the minus 6. Let's see, a farad is an amp second per volt times 2 kiloohms. So that's 2 times 10 to the positive 3. And an ohm is a volt per amp. Let's look at what happens with the units here. So this volts in the numerator cancels this volts in the denominator. This amps in the numerator cancels this amps in the denominator. So it looks to me like we're going to have, let's see, 600 times 10 to the minus 3, which I believe is 0.6. So 1 over 0.6 seconds. 1 over 0.6 is, so let's see, 0.6 is 3/5, so the reciprocal of 3/5 is 5/3. So I'm going to have negative 5/3 t volts for t greater than or equal to 0 plus. So before we move on from this little part right here, anybody have any questions about me, I guess, kind of calculating that rate of decay? Okay, so we know what the capacitor voltage was doing as a function of time, but we were asked to figure out what our resistor current was doing as a function of time. So knowing what the capacitor voltage was, how would we get that resistor current? Let me maybe help you guys out here. So we just figured out what this voltage V of C, excuse me, VC of T is. Using that voltage, how would we get IR?
Ohm's law.
Ohm's law, absolutely right. So IR of T is just VC of T divided by 2 kiloohms. So that's going to look like 8/3 of a milliamp and 8/3 e to the minus 5/3 t milliamps for t greater than or equal to 0 plus. So before we move on from this problem, I want us to think about something, and particularly with these results right here, right? So earlier on, we derived that the capacitor voltage during the transient condition would be of this particular form that I've just underlined, right? If we look at our circuit, and we were to look at, let's say, the voltage drop across the 2 kilo ohm resistor, positive polarity on top, negative polarity on bottom, what would that be in terms of VC?
Would it be the same thing?
It would. They're connected in parallel. That 2 kilo ohm resistor and the capacitor are in parallel, so the voltages have to be literally the exact same thing. Okay, which is why we were able to just use Ohm's law to figure out what that resistor current was. So the voltage drop across the resistor has to be of the same general form as the voltage drop across the capacitor, meaning it's an exponentially decaying thing because of Kirchhoff's voltage law. We know that the resistor current is an exponentially decaying signal, and it's exponentially decaying at the exact same rate as our capacitor voltage was because we just did that with Ohm's law. What do you think is going to be going on with the capacitor current? So just to kind of speed this up a little bit because we've got some things to do, right? If I applied KCL at the top node here, I would have IR of t plus IC of t is equal to 0, which means IC of t is just negative IR of t. So since our resistor current is exponentially decaying, our capacitor current has to also be exponentially decaying. So what I'm getting at here is that because our energy storage element, or at least the voltage drop across our energy storage element in the case of a capacitor, is behaving such that it is experiencing an exponential decay, everything that's connected to the capacitor is going to have that same general response. Doesn't matter if it's a voltage or a current, everything is going to be exponentially decaying. So what we've just found is that generally for any particular signal y of t, where y could represent a voltage drop or a current, it will have the value of y at 0 minus for t less than 0 minus, and it'll have a value of y at 0 plus e to the negative t divided by rc for t greater than or equal to 0 plus. Meaning that we don't necessarily even have to think about things to do any circuit analysis. So like right here, when we found IR of t using Ohm's law, let's see what happens if we literally just use the information from the table and plug stuff into this generic form, right? So IR of t. So what was IR at 0 minus? Scroll up so you guys see it.
8/3.
8/3 of a milliamp. What was IR at 0 plus?
Eight-thirds.
What was negative 1 over RC?
Five over three.
Yep. So negative 5/3 T milliamps for T greater than or equal to 0 plus. So doing this method of literally just plugging things into this generic equation gives us the exact same results as actually doing circuit analysis. So I would argue that this is the way that we should do things because it doesn't require any thought whatsoever. It's literally just take the information that we got from our various steps, plug it into this general equation, and we get the right answer. So that's the method that I would suggest that you guys employ from here on out. All right, so before we move along from our RC circuit, are there any questions or any points of confusion or anything? Or at least any points of confusion that you guys are willing to talk or ask about? All right. So now we'll circle back around and we're going to do something very similar, except that having instead of having a resistor and a capacitor, now we're going to see what happens when we have a resistor and an inductor together. So let's say that I have the following circuit. I am intentionally not labeling this resistor right here. I just want to be clear about that. So this is a similar circuit to what we just dealt with, but instead of having a capacitor, it now has an inductor. So I think that we should be able to figure out what's going on at t is equal to 0 minus fairly easily. Anybody have any thoughts on what our inductor current at 0 minus would be?
0.
So I disagree. What does a inductor look like to a DC circuit?
Be infinite. It's a short circuit.
So it's a short circuit. So at t is equal to 0 minus, our circuit would look something like this, right? So we have IS, we have our unknown resistance, we have our arguably known resistance, and then over here on the right, we have a short circuit. And we're trying to find the current that's flowing through, sorry, that should be a 0 minus, our short circuit. So I disagree that it will be 0 amps, and I also disagree that it will be an infinite amount of amps. Anybody have any other thoughts?
It'll just be equal to IS.
Exactly right. So we have a similar situation as to what we saw with our RC circuit. Because the current flowing through our inductor is non-zero, there is some amount of energy being stored by our inductor. Once that switch opens, disconnecting the current source and that left unlabeled resistor, the right resistor, labeled as R, will gradually convert all of the stored energy in the inductor into heat. Okay? So the situation that we have, even though it's a completely different type of energy storage element, is almost exactly the same. So we are going to skip or gloss over some of the parts here because this circuit is behaving almost exactly to the RC circuit that we discussed earlier. All right, so we know what's going on with the inductor current at t is equal to 0 minus. What should happen to the inductor current at t is equal to 0 plus?
Would it be 0?
It will not be. So last Friday, when we were discussing inductors, we learned two things when we were looking at the derivative-based relationship, right? So the first thing we learned is that an inductor in a DC circuit behaves like a short circuit, which we just used to find this current. And the other thing that we learned is that the current flowing through an inductor cannot change abruptly. So if the inductor current was IS at t is equal to 0 minus, what does it have to be at t is equal to 0 plus?
IS.
Exactly right. The inductor current can't change. All right, so now at t is equal to infinity. So this represents a point in time very long after our switch is opened, and we are assuming that all of the energy that was stored by the inductor has been converted into heat by our resistor. So we would expect to see that our inductor current dies down to 0 at t is equal to infinity. Okay, so we have an idea of what's going on in our system, and so now we're going to figure out how our inductor current behaves during the transient, just like we did for our capacitor voltage several minutes ago. So for t greater than or equal to 0 plus, our circuit will look like this. So we've got our current source connected in parallel to that unknown resistor. Our switch is open because we're after the time where our switch opened up. Here's our resistor R. Here's our inductor L. Here's our inductor current IL of t, like so. So what I'm going to do is I'm going to label the voltages that our inductor current is going to see in its path. So we're going to have a voltage VL of t, like so. And then I'm going to have a voltage VR of t, like so. And I've put the positive polarity terminal of the resistor voltage on bottom so that the current IL of t will flow into the positive polarity terminal. Okay. So if we were to apply KVL around our right-hand loop, what we would get is simply VR of t plus VL of t is equal to 0. And we can express both of those voltage drops in terms of our inductor current, IL. So using Ohm's law, we would have R times IL of t. And then using our first equation from when we were learning about inductors, the voltage drop across an inductor is given by L times the derivative of the inductor current with respect to time. And so what we have is another linear homogeneous first order differential equation. So since guessing that our waveform would be an exponentially decaying signal worked so well for us last time, we're going to make the exact same guess here to solve the same type of differential equation. So if we guess that IL of t is an exponential AE to the negative, excuse me, AE to the ST, my apologies. And we plug that guess into our differential equation, what we wind up getting is A times R e to the ST plus S times A times L e to the ST is equal to 0. And we can rearrange that just like we did earlier. So we'd have A and a common factor of e to the ST. And in the middle, we would just have R plus SL, where this R plus SL is our characteristic equation for this type of system. So we have R plus SL is equal to 0, which means S has to be equal to what?
Negative R over L.
Negative R over L. So, revisiting our guess, we now have IL of t is equal to AE to the negative R over L times t. We know that at t is equal to 0, we are just going to have AE to the 0, or A. So that means that our inductor current will generically be IL at 0 plus, since all of this derivation is for t greater than or equal to 0 plus, e to the negative R over L t. So effectively, it's almost the exact same expression as our capacitor voltage, except that now our rate of decay is dependent on the inductance and the resistance as opposed to the capacitance and the resistance. So how do you think this is going to change our steps in our analysis procedure? Effectively, anywhere we were asked to find a capacitance, we just find the inductance. Everything else is literally the same. Okay. So let's look at in-class assignment problem 1. Okay. So in this particular problem, we are asked to find our current I of t, which happens to be the inductor current, and we're also asked to find this voltage V of t, which is the voltage drop across the 4 kilo ohm resistor, positive polarity on top. Okay. So applying our 5-step process, we're going to analyze our circuit. At t is equal to 0 minus. So that would mean that we have an 18-volt source, a 4 kilo ohm resistance. So at t is equal to 0 minus, we're at DC steady state. So our inductor is now going to look like a short circuit. So that's why I'm just drawing a wire here. Here we have an 8 kilo ohm resistor. Here is our current, IL of 0 minus. Here is our voltage, V of 0 minus. Could anybody tell me how we might solve for either of those two quantities?
Since it's in parallel, won't the voltage drop just be 18?
Exactly right. Any thoughts on the inductor current?
I think the easiest way would just be current division.
So current division is useful when we have a known current dividing between two resistors in parallel. But we don't have a known current, we have a known voltage. So I would argue Ohm's law. We know the voltage drop across the 8 kilo ohm resistor is 18 volts because the 8 kilo ohm resistor appears in parallel with a 4 kilo ohm resistor when our inductor is behaving like a short circuit. So I think it'll just be 18 volts divided by 8 kiloohms, which would be 9/4. So 9/4 milliamps, which does equal 2.25 milliamps, by the way. Does that make sense? Let's start there.
Yes. Yeah.
Okay. All right. So does anybody have any questions regarding step 1 before we move along to step 2?
I'm a little confused on the current part.
Sure. So let me come back to our original circuit up here just so we can see things, right? So this current I of T is the same current that's flowing down into the 8 kiloohm resistor. Do you agree with that?
Yes, sir.
Okay. So we learned, or actually, let me put it this way. So the voltage drop across an inductor as a function of time is the inductor value times the derivative of the inductor current with respect to time. So at t is equal to 0 minus, that's when our switch was closed for a long time before opening at t is equal to 0. So that means that in our original circuit, we're at a place where that switch has been closed or just a short circuit for a very, very long time. So what we're looking at is essentially a DC circuit where our inductor is treated as if it were a wire. Okay. So that means I have this 18 volt source connected in parallel to this 4 kilo ohm resistor connected in parallel to this 8 kilo ohm resistor. Since all of them are in parallel, I know that the voltage drop across the 8 kilo ohm resistor is 18 volts. And so using Ohm's law, 18 volts over 8 kilo ohms is 9/4 of a milliamp.
Okay, yes, sir.
Any other questions about our analysis at t is equal to 0 minus? All righty. So now we're going to look at what's going on at t is equal to 0 plus. So at t is equal to 0 plus, our switch will be open. So that is disconnecting the voltage source from the network to the right. Okay. So we're going to have our 18 volt source, an open circuit. Here's our 4 kilo ohm resistor. Over here is our 8 kilo ohm resistor. And now let's talk our way through what we should do with the inductor. So our inductor current at t is equal to 0 minus was 9/4 of a milliamp. So what does our inductor current at 0 plus have to be?
9/4 of a milliamp.
Exactly right, because our inductor current cannot change abruptly. So we know for sure that the current that is flowing through the inductor is 9/4 of a milliamp, and the voltage drop across the inductor is whatever it needs to be to make that happen. So we are going to replace our inductor with a current source having the same magnitude and direction as our inductor current at 0 minus. So I'm going to have a current source direction to the right that has a value of 9/4 of a milliamp. So this is very, very similar to what we did for capacitors, except that for a capacitor, because it's the voltage drop that doesn't change, we replace it with a voltage source. In an inductor, we replace it with a current source at t is equal to 0 plus. So now our goal is to find this voltage at T is equal to 0 plus. Does anybody have any thoughts on how we might do that?
KVL. Or no, Ohm's law.
Ohm's law. Okay, so tell me what that should look like, please.
It would be 9/4 of a milliamp times -4 kilo ohms.
Exactly right, because the current's flowing into the negative polarity terminal. So if I'm not mistaken, that's going to come out to be -9 volts. Does anybody have any questions about step 2 in our RL circuit? All right. So step 3. We're going to analyze the circuit at T is equal to infinity. So at T is equal to infinity, we're once again at DC steady state. So my switch is still open. My inductor is going to look like a short circuit because it always looks like a short circuit at DC steady state. So that'll be 0, minus, and infinity. Always, always, always. So here's my inductor current. And here's my resistor voltage. And by inspection, we can see that both of these are going to be 0, which is what I mentioned earlier for today. Everything at infinity is always going to be 0. So we're just going to have 0 milliamps and 0 volts. Any questions about step 3? All right. So let me give myself some room here. So step number 4, we're now just going to find LEQ and REQ, right? So what should LEQ be?
12 millihenries.
12 millihenries, because it's the only inductor in the circuit, so it can't be anything else. To find REQ, we're going to look at the circuit, and let me just put here, during transient. So we're going to look at the circuit during the transient condition. So that means our switch is open. We are going to take our energy storage element out, look in through its terminals, and we need to make sure that we're looking at a dead network. So I'm turning that voltage source off. So what do I see?
$12 kilo ohms.
12 kilo ohms, exactly right. So just 4 kilo ohms in series with 8 kilo ohms looks like 12 kilo ohms. I know that nobody said this, but I know from prior experience that multiple students have thought that this should have been 4 in parallel with 8. So let me just explain quickly why that isn't the case. So if we identify our nodes here, we have this node, and this node. For the 4 kilo ohm resistor to be in parallel with the 8 kilo ohm resistor, it would have to be, they would both have to be between the red and the green or the blue and the green. But They are not. Only the 4 kilo ohm is between red and green. Only the 8 kilo ohm resistor is between blue and green. So because this node and this node aren't tied together, they are not in parallel. Again, I know that nobody asked for it, but I just wanted to be really clear about that. So step 5 will be to plug stuff into our generic equation. So for an RL circuit, our generic equation will be as follows. Y at 0 minus for t less than 0 minus, y at 0 plus, e to the negative r over L times t for t greater than or equal to 0 plus. Okay. So we are asked specifically for our current I of t and our voltage V of t. So let's do the current I of t first. So what was I at 0 minus?
Nine-fourths of a million.
Yep. So 9/4. What was I at 0 plus?
Nine-fourths of a milliamp.
Thank you, Leah. E to the negative. So let's come up here really quickly and figure out what R over L is. So R is 12 times 10 to the 3 volts per amp. L is 12 times 10 to the minus 3 volt seconds per amp. So 12 cancels 12, volts cancels volts, per amps cancels per amps. So this is going to leave us with 1 times 10 to the minus 6 per second. So 10 to the minus 6. No, I'm sorry, 10 to the positive 6. My apologies there. For t greater than or equal to 0 plus. And then for our voltage, what was our voltage at 0 minus? 18. Our voltage at 0 plus was -9, so it'll be -9 e to the negative 10 to the 6 volts for t greater than or equal to 0 plus. How do you guys feel about this?
Formula memorization.
For the most part, yeah. The circuit analysis part of these is just the same stuff that you've been doing. As long as you can remember that t at 0 minus and t at infinity always represent DC steady state conditions, meaning your inductors should look like short circuits and your capacitors should look like open circuits. It's just the same circuit analysis stuff that you've been doing. Then you just take all of the information and plug it into a generic formula. So I personally, I'm not trying to sound like more of a jackass than usual. I personally don't find this stuff to be particularly difficult. In fact, I rather enjoy it. I just want to make sure that all of you guys are getting it, because this material is going to make up a pretty large portion of your test. So if you look at the practice exams that I have uploaded, and I did that right before class, so you didn't miss anything. But anyway, if you look at the practice exams that I have uploaded, There's usually 2 transient analysis problems on each of the tests, and those transient analysis problems are broken down into 4 or 5 sub problems. Okay, so like 8 to 9 out of the 20 analysis problems that you're asked on your upcoming exam will be related to this material and what we're covering on Friday. So if this isn't clicking for whatever reason, please don't hesitate to ask questions, or if you don't want to ask questions in front of people, shoot me an email. We can set up a Zoom meeting, however you want to go over it. I'm happy to do so, but I want to make sure that you guys are all comfortable with this because it is damn near half of your exam grade that's coming up. So, all right. Technically speaking, we still have one last problem here at the end, so let's knock that out really quickly. Oh, let me see what's going on in chat here. Is there any math behind the milliamps? So let me scroll back up there. So the reason that we were getting milliamps, oh, that's the wrong problem. Sorry. Was simply because we were, volts per kilo ohms is giving us milliamps. Is there any math behind the milliamps for the 9? Actually, I think. So let me make sure that I'm understanding the question correctly, because I think I just misunderstood. So for this part right here, it's just 9/4 of a milliamp, nothing else, because we're looking at the circuit before our switch changed states. So because that portion of time represents a DC circuit, we shouldn't see anything else. Oh, I did notice though, I forgot to put a T here and a T there. So perhaps that's why it was confusing. I apologize for that. For this part right here, this represents what's going on over the interval from T greater than or equal to 0 plus. So this is when our system is changing as a function of time, which is why we've got that exponential decay term. Caleb, did that clarify things, or did I misunderstand your question? Okay. I apologize for forgetting to put the T there. All right, so let's pop back down to problem 3 really quickly. So we have an RL circuit. We are given the voltage drop across the inductor, and we are also given the current that is leaving the positive polarity terminal of the inductor. And so that is the same current that would be flowing into the positive polarity terminal of our resistor. Okay? We are asked to determine the value of the resistor in the circuit. Anybody have any thoughts whatsoever on how we might do that?
Couldn't you just use Ohm's law with the 2 equations given?
Absolutely. Doesn't need to be any more difficult than that. So R is simply our voltage drop divided by our current. So that is 20 e to the negative 10 to the third t volts divided by 4 e to the negative 10 to the third t milliamps. So we can see that the e to the minus 10 to the 3 t's cancel each other out. So it's really just looking like 20 volts per 4 milliamps, which comes out to be 5 kilo ohms. So nothing particularly wild or crazy there. In part B, we're asked to determine the value of the inductor. Anybody have any thoughts on how we might do that?
Use your V of t equals L DIL of t over dt.
We could definitely do that. However, I'm lazy. So instead, let's think about this, right? So actually, let's think about this one down here. So this is the current that's flowing through an inductor. So we know that it's of the form IL at 0 plus e to the negative r over L t. So this 10 to the third right here is r over L. So 10 to the third is equal to r over L means, that L is simply r over 10 to the third. So 5,000 divided by 1,000 is just going to be 5 henries. If I can avoid using calculus, I'm going to. Which actually brings me to part C. So part C asks us to determine the energy dissipated by the resistor over the time interval from 0 plus to half of a millisecond, okay? So I'm going to hit you guys with 2 different ways to do this, and then I'm only going to actually do the math for one of them, all right? So we're looking for energy. Energy is the integral of power, right? So we could have the integral from 0 to 0.5 milliseconds of the product of V of t and I of t with respect to time. There is nothing remotely wrong with doing this, okay? Other than it involves calculus and I am lazy. So how I am going to do it is to think of it in this way. So the energy dissipated by the resistor over that time interval has to be the same as the energy lost by the inductor over that time interval. So if we were to find the energy stored by the inductor at 0 plus and subtract from that the energy stored by the inductor at half of a millisecond, that is going to be the exact same thing as the energy dissipated by the resistor over that interval. And the reason why I'm using this approach is, once again, I don't have to do any calculus to do it, and I'm really lazy and I don't like integrals. So WL at 0 plus is just 1/2 times our inductor value of 5 henries times our inductor current at t is equal to 0, which is just 4 milliamps, squared. Let's see. 0.5 times 5 times 4 times 10 to the minus 3 squared comes out to be 40 microjoules. WL at 0.5 milliseconds is going to be 1/2 5 henries 4e to the negative 10 to the 3 times 0.0005 milliamps squared. So let's see, 1,000 times 0.0005 should be just 0.5, I think. Yeah. So 0.5 times 5 times 4e to the negative 0.5 quantity squared comes out to be 14.71517, so 715 microjoules. And so that difference is 40 minus that answer, 25.285 microjoules. Just for the sake of argument, because I have -1 minute, so I'm going to make you guys suffer through my BS for just a moment here. If I multiply these two things together, so 20 times 4 is going to look like 80 milliwatts. E times 10 to the minus 3t times E times 10 to the minus 3t is going to look like E2 times 10 to the minus 3t dt. If I threw that in my calculator, because I'm too lazy to do that integral by hand, I just got the 14.715 thing. I must have put something in the calculator wrong. But anyway, it should wind up giving you the exact same result. Because you're just doing the exact same thing. You're just approaching it from two different ways. So, all right. I apologize for running a couple of minutes long for today. I will endeavor to get the video up possibly tonight, definitely tomorrow morning. Like I mentioned earlier, you have multiple practice tests that are available to you all. So if you have any questions about anything, please let me know. And I hope you have a great rest of your afternoon. Thank you.
Dr. Hartman,
Yes.
I was wondering if I could set up a Zoom meeting with you tomorrow to go over stuff.
Yes. However, really the only time that I have tomorrow specifically, I think will be between noon and 1, because in the morning I have a College of Engineering and Science leadership team meeting. And in the afternoon, after 1 p.m., I'm helping with the freshman orientation. I'm more than willing to meet with you during that time window, but that's the only time that I have tomorrow.
I mean, we could do Friday as
Okay.
well.
So Friday, I think I should have some time between 9 a.m. and 11 a.m. And then again, let's see, then I have to pick up my dog from the vet, drive home. So between 9 and 11, and I think after 1, I should be free. Sorry, this week has just been very busy for me.
Yes, sir. I'll shoot you an email.
Okay. Thank you so much.
Thank you.
Dr. Hartman,
Yes.
Could you go over one of my web work problems for me?
Absolutely. Which one would you like assistance with?
Homework 11, problem 4/5, I guess, really.
All right, let me pull up web work real quick. Is not spelled right. Homework 11, and you said numbers 4 and possibly 5.
Yes, sir.
And let me do it this way. So that was homework 11, problem 4. Okay. So, and let me write this down. Homework number 11.4. So in this particular problem, we have a current source where we have some current IS of t connected in series with a 10 ohm resistor, and then connected in series with a 5 Henry inductance. We are told that we are trying to find this input voltage as a function of time when IS of t is given by the expression 2.7 t squared for t greater than 0, and we want Vn for t greater than 0. So I mentioned this, I think, at the end of our last class meeting, but whenever I see a circuit like this where everything is connected in series, it tells me to apply Kirchhoff's voltage law. So I'm going to define the voltage drop across my resistor as VR of t, and define the voltage drop across my inductor as VL of t, like so. And then using Kirchhoff's voltage law, Vn of t is just VR plus VL. Using Ohm's law, VR is just our resistor times IS of t. And using our first equation for inductors, the voltage drop across our inductor will be L times d IS by dt. So if we plug in the parameters from your particular version of the problem, let's see, 2.7 times 10 is going to be 27 t squared. And then we're going to have 5 times, let's see, we just need the first derivative. So 2 times 2.7 t, so that's another 10 times that. So 27 t squared plus 27 t volts. If my calculus is correct, which is always a question.
All right, and that would just be the answer.
Yes, because we're just looking for things as a function of time. Let me just double check.
Okay.
Yep.
That's where I guess I got confused on this one. I thought it wanted just a straight numerical answer.
No, so it was very specifically looking for a mathematical function. Yeah. Let me look at problem 5. Problem 5 is a similar thing. It's looking for In as a function of time valid for all t greater than 0, so it's looking for a function as well. Looks like you do have a function put in here. So let's look at it really quickly if you have a moment.
Yeah.
So we've got this voltage Vs of t, this current In of t that we're looking for. Here's a 10 ohm resistor. Here's that same 5 Henry inductor. And then this is IL of t. We're told that Vs of t is 40 t volts for t greater than 0. We are told that IL of 0 is 9 amps, and we're looking for In of t for t greater than 0. So I'm going to apply Kirchhoff's current law, where this is going to be my resistor current. So I can say that In of t will be IR of t plus IL of t. Using Ohm's law, IR is just Vs of t divided by R. And using our integral-based relationship, I can say that IL is 1 over L times the integral from t naught, which in this case is going to be 0, to t of Vs of t plus IL at 0. So let's see, 40t divided by 10 is going to look like 4t plus 1 over 5 times integral of 40t prime from 0 to t plus 9. So let's see, I'm just going to do stuff. So here's the 9, here's the 4t. 40 over 5 is 8. So 8t squared over 2. So 4t squared. That's it.
All right. Yeah, okay.
Yep.
Speed the 20. Okay, yeah. All right. Well, thank you very much.
No problem. Anything else?
That is it for now.
Okay. If you have any further questions, please don't hesitate to shoot me an email or a text or whatever.
All right. Thank you very much.
No problem. Have a great rest of your afternoon.
You too.
All right. Gonna end the Zoom because we're 13 minutes over. Like I said, if you have any questions about anything, please let me know.